In this video we're going to be talking about some angle sum identities. Now the first of these, cosine of A plus B equals cosine A cosine B minus sine A times sine of B, is actually a little harder to prove than the rest, and it's covered in an earlier video, and it uses this page here of the sketch. But we're going to use it to help us prove all the rest of these identities. So the first one here is a group of double angle identities, three different forms that we can write cosine of 2a. I guess four forms if you count cosine 2a itself. So here's the proof here. So we start with our identity 1 that says cosine A plus B equals cosine A times cosine B minus sine A times sine B. And we just simply let A equal B. So we do that substitution, and then it becomes cosine A plus A equals cosine A times cosine A minus sine A times sine A. A plus A is 2A. That's just the definition of multiplication. And cosine A times cosine A is cosine square A, and sine A times sine A is sine square of A. That's just the definition of what it means to be a second power. And so that proves identity 2a, that cosine of 2a is cosine square A minus sine square of A. We could also change everything to just cosines or just sines. So we could, for example, change sine square of A to 1 minus cosine square of A. We get that from taking cosine square of A plus sine square of A equals 1, our basic Pythagorean identity, solving for sine square of A, and we find that sine square of A equals 1 minus cosine square of A. Put that in place of the sine square of A. Now we distribute the negative 1, and that gives us cosine square of A minus 1 plus cosine square of A, and of course cosine square of A plus cosine square of A is 2 cosine square of A. And so we combine like terms there. Basically we're really using the really a combination of the commutative, associative, and distributive properties, really, to put all that together. And so that becomes cosine of 2a equals 2 cosine square A minus 1. Now, we can also go back to the original identity, take cosine of 2a, and say that that's equal to cosine square A minus sine square A again. But this time we apply the Pythagorean identity to that again. But this time we replace the cosine square of A by 1 minus sine square of A. So we're going back not to the previous line here, but to the line up here. Cosine square A minus sine square A, and replacing cosine square A as 1 minus sine square. And then this becomes, we combine like terms here, and that becomes 1 minus 2 sine square of A. So we have basically four nice forms here. One is cosine of 2a, and that's also equal to cosine square A minus sine square A. We could also write it as 2 cosine square A minus 1, or 1 minus 2 sine square of A. I guess we could also even factor that difference of two squares and make it cosine of A plus sine of A times cosine of A minus sine of A. So those are the double angle identities for cosine. Now we're going to get an angle sum identity for sine. We already had derived cosine of A plus B equals cosine A cosine B minus sine A sine B. And we're going to see that sine of A plus B is cosine A sine B plus sine A cosine B. Okay, to prove that, we're going to use our phase shift identity. Sine of an angle is cosine of that angle minus pi over 2. So sine of A plus B is cosine of A plus B minus pi over 2. We're going to use the associative property and regroup that. So instead of grouping the A plus B together, we're going to group the B minus pi over 2 together for our next part right here. Now, we're going to use the cosine identity here, number 1, and so that's cosine of the first thing in here times cosine of the second thing minus sine of the first thing minus sine of the second. So that's cosine A, cosine of B minus pi over 2, minus sine of A times sine of B minus pi over 2. Cosine of B minus pi over 2 is the same phase shift identity we used in the first step. Using it the other direction, this becomes sine of B. Now, okay, so we just did that. Now this next part here, I'm going to factor out a negative 1 out of this and make B minus pi over 2 into minus 1 times pi over 2 minus B. So that's just the distributive property and commutative property there. Now sine is an odd function, so sine of minus x is the opposite of sine of x. So this minus here basically cancels out, or comes out, and it's going to cancel that minus out and make a plus. So now we have cosine A sine B plus sine A times sine of pi over 2 minus B. And we have a cofunction identity that we covered earlier, and this is going to tell us that this sine of pi over 2 minus B is the cosine of the B. And so we have what we desired to prove, that sine of A plus B equals cosine A sine B plus sine A cosine B. So now we have an angle sum identity for cosine of a sum. We have an angle identity for sine of a sum. We took the cosine of A plus B, replaced B by A, and got double angle identities. Well, in a similar way, we're going to get this identity for sine of 2A. This is a short proof here. We start with our previous property number 3, sine of A plus B equals cosine A sine B plus sine A cosine B, and we just substitute B equals A. So all the B's become A's. On the left side, that gives us sine of A plus A, which is sine of 2A. On the right, we get cosine A sine A plus sine A cosine A. Well, sine A cosine A is the same thing as cosine A sine A, and so these add up and double up there and become 2 cosine A sine A. Now I'm going to go back and take 2B and 2C and solve them for the square term, and that's going to give us what we call power reducing identities. So let me do this first one here. So I start with 2b, cosine of 2a equals 2 cosine square a minus 1. And I'm going to add 1 to both sides and divide both sides by 2, and I get cosine square of a equals 1/2 parentheses 1 plus cosine of 2a. In a similar manner, we have another power reducing identity. This time we take 2c, cosine of 2a equals 1 minus 2 sine square of a. Solve that for the sine square there of a. So we subtract 1 from both sides, divide both sides by negative 2. So I'm going to distribute the negative 1, that makes it 1 minus cosine of 2a, and just leave the 1/2 out front. So we get sine square of a is 1/2, parentheses 1 minus cosine of 2a. So notice this allows us to take something that's a square, say a cosine square or a sine square, and then get it down to something that's a first power. When we do that, the angle inside, or the input, doubles. So we're using our double angle. It's really the double angle identity again, sort of written around in a different form. Now these 5 and 6 are particularly useful in a certain step in calculus problems, when it's useful to, well, it turns out the calculus step you want to do is pretty easy to do on a cosine of, well, it doesn't matter what the coefficient is there, but we need the first power. Second power is not so good. Well, this allows us to get to something we can proceed with. So sometimes we want to be able to do that. You can also take the square root of both sides here and solve for cosine A, but then you have to be careful because you don't know whether to take the positive or the negative square root. It depends on the value of A, the sign of cosine of A, basically which quadrant that terminal side ends up when you're thinking of the unit circle picture. Now, tangent of A plus B, well, when in doubt, what do? Change to sines and cosines. So the first thing we're going to do is say tangent of A plus B is sine of A plus B over cosine of A plus B. That's our quotient identity. Now we can use, on the numerator, we're going to use property 3. Sine of A plus B is cosine A sine B plus sine A cosine B. And in the denominator, we're going to use property 1, that's cosine of A plus B becomes cosine A cosine B minus sine A sine B. Now what we're going to do is we're going to multiply top and bottom of this fraction by 1 over cosine A cosine B. And of course that distributes, and it makes little fractions, 2 little fractions in the top and the bottom of the big fraction. So when I distribute, we get cosine A sine B over cosine A cosine B plus sine A cosine B over cosine A cosine B. And similarly, we get something like that in the bottom. Now we just cancel out the like factors in the top and bottom, our fundamental equivalence property of fractions. So we cancel out the cosine A's and we get sine B over cosine B here. Here the cosine B's cancel, you get sine A over cosine A. Here everything cancels, so you just get 1. And nothing cancels here, but I'm just going to group it as sine A over cosine A and sine B over cosine B, because that's how we multiply fractions, sort of going backwards. Now we use our quotient identity. Sine B over cosine B is tangent of B. I'll put that one second. Sine A over cosine A is tangent of A. I put that one first. And this is sine A over cosine A is tangent A. Sine B over cosine B is tangent of B. So I use my quotient identity there 4 times, and we get the result that we wanted, that tangent of A plus B is tangent of A plus tangent of B over 1 minus tangent of A, tangent of B. Notice that when we're proving identities, we start with one side of the identity. We do a series of transformations to the other side until we end up with what we want. But we must give a justification or reason for every step along the way. That is a proof of an identity. So if we want to prove tangent of 2A, we start with our previous one of tangent of A plus B is tangent of A plus tangent B over 1 minus tan A tan B. That's the identity we just proved. And we just once again substitute B equals A, turn all the B's into A's. And so in the top we have tan A plus tan A is 2 tan A. In the bottom we have two tangent of A's multiplied together, so that becomes tan square of A. So tangent of 2A is 2 tan A over 1 minus tan square of A. And of course you can see the reasons here. The first reason for the first one is just our identity number 7 that we already proved. The next one is just doing a substitution. Then really what we're doing is just x plus x is 2x, that's the numerator. And then x times x is x squared, that's the denominator, what we use there. And those are really just the definition of what 2 times something means and what something to the second power means. And so we have now proved these basic angle sum and double angle identities.